In chapter 15, we're going to learn about chemical kinetics. Now, chemical kinetics basically means the movement of the molecules with respect to time. How fast is the reaction occurring, and reaction rate. So what is the reaction rate? The reaction rate is the speed of the reaction, and it can be measured by the concentration change of either the products or the reactants, because as the reaction goes forward, reactions or reactants are going to decrease and they're going to form products which will then increase. So here's a very simple reaction where you have reactant A yields reactant B. It changes to another substance. Now, if you look at the reactant and product concentration percentages in terms of total moles in the sample, you can see that as the reactant A is being removed from the sample, meaning as it's being converted to product B, the concentration percentage of the entire solution equals 100%. As it decreases, as reactant gets turned over to product, at the exact same time, product B is increasing. So we see this kind of decrease of the reactants, increase of the product. So this chapter, we're going to learn how we can define this and use it and mathematically figure it out as a term of molarity per second. That's really going to be the main unit, molarity per second. So how fast does the concentration change? So we can define the rate as being the change in concentration over change in time. Now, for reactants, that rate is always going to be expressed negatively because the change in the reactant concentration is always going to decrease as the reaction goes forward. This means the rate is going to be the negative of the change in concentration of the reactant over the change in time. Whereas for the product, it's going to be positive because you're going to be creating more product as the reaction goes forward. Now, you can look at this just a schematic of what happens when you have a slow reaction versus a fast reaction. And we're going to be able to calculate how fast the reaction is, what we just talked about. Now, another way you can determine the rate of reaction based on concentration of products and concentration of reactant curves is within a function of time is by using a little bit of calculus and calculating the tangent line. So the tangent line at a certain point would give you the slope at that point. And the slope is going to be your rate of change, right? So the slope is the change in your y versus your change in x. In this graphical context, the change in y is going to be your concentration in molarity. So molarity, and then your change in x is going to be your time. So molarity per second. And that's another way graphically, if you're given a graph, you can figure out the reaction rate of either the products increasing or the reactants, which would be decreasing. And something you might be thinking of is how does the reaction rate change based on the coefficients that are in a balanced equation? And that's a good thought, but we'll talk about that more later. And there's equations that govern that as well. So to calculate the average rate, you can just say, you can do a linear approximation of a curve. So let's say we looked at the curve up here, and we want to determine the average rate of the reaction from, let's say, 30 seconds all the way to 80 seconds, right? We would take the 2 points, 30 and 80, and do the change in y over the change in x, and we would have a slope going from 30 seconds to 80 seconds. And that would be a decent approximate. I mean, if you go, the larger the time interval, the worse approximate it is. But overall rate, it would tell you. But there's a better way to represent this rate because, look, it's constantly changing over time. And that's based on what order of a reaction it is. So we can talk about that more in a few slides. Now, the instantaneous rate, that was the average rate where you take 2 points, but the instantaneous rate can be figured out by a derivative. So we're not going to talk about derivatives in this class. That's calculus, which you already hopefully had. But basically, it's the slope at the tangent line. So at a specific point on a curve, what is the slope of that point? So that's how you can figure out the instantaneous rate. Now, here is a very important equation. This can relate the coefficients of the reactants and the products to their reaction rate, or to their concentration change and to the rate of the entire reaction. So let's look at this reaction. H2 plus I2 equals 2HI. Now, what's happening? A lot of this is happening. So let's read this bold statement. Every mole of I2 used needs to form 2 moles of HI. So it forms twice the amount of product in the same amount of time, because once this is completely removed, once the one mole is gone, the 2 moles will be completely formed, meaning this process of the reactants decreasing and the products increasing happens in the same amount of time. This means that the rate at which HI forms per mole, meaning the concentration increase, has to be double the rate of the disappearance of I2 in order for it to catch up to, so basically saying the time that 1 mole of I2 is removed or it goes away is the same time that 2 moles of HI need to be made. Therefore, the reaction rate or the change in concentration of HI is double. So that can be represented, and we can actually talk about the rate of the entire reaction in terms of the rate of disappearance of reactants or appearance of a product. So for this example, or for any example, you'd have the rate equals, let's say you had reactants A and B and products C and D. The rate would be 1 over the concentration change of A over the time, and then it would be negative, right? And then for the products, it would be positive, right? Because the products are being formed. So you can take some time to think about that. Now, here's a conceptual question. For the reaction A plus 2B equals C, under the given set of conditions, the initial rate of the reaction is 0.1 moles per second. What is delta B? So what is the change in concentration of B over time? So B is being removed, right? It's a reactant, therefore it must be negative. So it's either A, B, or C. And let's write this down. Let's write down what we know based on the equation we just saw, is that the initial rate of reaction is 0.1 molar per second. And this can be equal to 1 over the coefficient of B, we'll call it little b, times the concentration of B over the change in time. But we already know that the coefficient, so we can just figure out what is the delta B over delta T. So the coefficient of B is 2. So put a 2 there, multiply 2 by both sides, we get 0.200 molar per second is the change in concentration of B over time. Now it has to be negative because B is a reactant. So the answer is C. Okay, so I'm going to skip these for now. This is a brief overview of the chapter, so I'll skip those. Let's talk about the one of the 2 main factors that contributes to the reaction rate, one of which is the concentration of reactants. So you can imagine, based on what we learned in Chem 1, where we talk about the speed of molecules leading to more collisions. We're going to learn more about that today. Is that the speed of the molecules actually, and the amount of molecules, can actually determine the rate and actually increase the rate in some cases. So the general rate law we talk about is rate equals K times the concentration of A to the n power. So n is called the order. So whether that order has to do with the coefficients, but just talk about it as the order. And K is the rate constant. So it's usually per second or per minute. In this case, where A yields a certain amount of product. So the rate of a reaction is dependent on the concentration of reactants, but it gets a little bit more complicated. There's different orders of equations. So n is this order. Now we can talk about order. For an example, if we have our rate equals K times, in some reaction that's not written here, NO, or it would be 2NO plus O2, then our reactants, it would be NO squared plus the concentration of, or times the concentration of O, and our exponents, meaning there's a 1 here, our exponents added up would equal the order of the reaction. So order of the rate law. So a very key component, if you don't want to get too crazy with this, add up the exponents for the rate law. That determines the order of the rate law. Very important, because a lot of questions will be asking you to figure out the rate law. And what can knowing the rate law tell you? It can tell you that if the rate law is 0 order, meaning this n is 0, that means the rate law, the rate is just based on K. This turns to 1. The concentration of A to the n becomes 1, and then rate equals K. So what that means is if you double the concentration of A, nothing will happen to the rate. Nothing will happen. More products will be made, but the rate at which they're produced will be identical. So it'll be basically a straight line until the reaction's done, then it becomes 0. If it's first order, meaning this is a 1 here, what that means is the rate is directly proportional to the reactant concentration. So if you double A, rate doubles. If it's second order, meaning N is 2, or the sum of the coefficients of this reactant and another reactant are 2, that means the rate is directly proportional to the square of the reactant concentrations, meaning if you double A, you'll quadruple the rate of the reaction. So there's actually a lot of equations that are, we see 0 order, first order, and second order. So here's how they look graphically speaking. The rate of concentration of reactants versus time, where the concentration of 0 order, the reactants just decrease linearly. First order, they decrease, and then the decrease slows down as concentration decreases. And then for N equals 2, the rate slows down faster because you're more related, you're more dependent on concentration. And then the rate of products being, or rate versus, this is concentration. This is the rate of the reaction versus the reactant concentration. So 0 order, doesn't matter what the concentration of reactant is, it's flat. If you have an increase in concentration for first and second order, the rate of the reaction would increase, but in different manners. By one is exponential and one is linear. So here's another conceptual question. For a particular reaction in which A equals products, doubling the concentration of A causes the reaction rate to double. What order is the reaction? So if doubling the concentration causes the rate to double, not quadruple or not change at all, but to double, then it's first order. So how can we determine initial rates? So we can determine these rates from data tables that are presented to us, or we can use the integrated rate laws. So there's a lot of questions on the homework relating to using the experimental data, where we would just do concentration 2 minus concentration 1 over time 2 minus time 1, which, I mean, we can do that, but those are pretty simple. But the rate laws are what we want to get after. Now, there's going to be a whole set of rate law equations for 0 order, first order, and second order, but you do not need to memorize them. I would say you need to be familiar with them and be familiar with the units, because the units for the rate constant for the 0 order, first order, and second order are different. So for a first order rate law, we'll do the easiest one first. What we have is that the rate equals K times the reactant concentration to the 1. The integrated rate law, how do we figure that out? We integrate this. Basically, if you do the integral, and the derivation for it is right here. So I'm not going to go over the derivation, but here's a link to it. You integrate that, and then you try to solve for, make it linear. So you can do an y equals, this is kind of y equals mx plus b. You can calculate that the natural log of A equals negative kt, where negative k is the slope of the resulting graph, plus the natural log of the initial concentration of A. So again, we don't need to memorize this, but it is the first order rate law, integrated rate law. So what we can say is that, like I said, the graph of the natural log of A over time is a straight line, and the slope is negative k based on this y equals mx plus b. So it's important to understand what the rate law means. And the y-intercept is going to be the natural log of A initial. So you can figure out the initial concentration in that reaction for if you know it's a first order rate law. So what this means is that the rate constant is going to be in per second, because you have the rate is going to be molarity per second. So here's what a first order integrated rate law looks like, where natural log of the initial concentration of A is the y-intercept. Next, so a reaction A to B has experimentally determined to be second order. So think about that. Second order, you automatically think, all right, I doubled the concentration of the reactant, I quadruple the rate law. So what do we say? The initial rate is 0.01 molarity per second at an initial concentration of A equals 0.1. Okay, so the rate of the reaction is 0.01 at an initial concentration of A of 0.1. What is the initial rate at 0.5? Okay, so we can calculate this. The initial rate is 0.01, and this is going to equal, since it's a second order, is going to equal the rate constant times the concentration of A squared. So that means our 0.01 is going to equal K 0.1 squared. We can use this to solve for our rate constant. And then we can use that number to figure out the initial rate at A equals 0.5 molar. So our 0.1 squared is 0.01. So we have K times 0.01 equals 0.01. This means K is equal to 1. So if that's the case, if our initial rate is 0.5, so we have K times 0.5 squared equals our rate, then we know K is 1. We can just say that 0.5 squared times 1 is 0.5 squared, so 0.25. And that's going to be our rate. So that would be our answer. Okay, so you can also determine the rate law when there's multiple reactants. And there's an overall order, right, as you add up the exponents. Now, here's a question. You could say that this reaction was experimentally determined to be first order with respect to O2 and second order with respect to NO. Most of the time they follow the coefficients actually, but if you're stuck, you can try that, but not all the time. The diagrams shown here represent reaction mixtures in which the number of each type of molecule represents its initial concentration, which molecule is the fastest initial rate. So if it's second order with respect to NO, this means that the more NO there is, the faster the rate will go. It has more dependency on NO than it does for O. So if we look here, O2, there's 3 and 3. Here there's more O2s, and here there's more NOs. So therefore, the one with the more NOs will go faster because the rate law has more of a dependence on 2 because it's just, or on NO, because it's NO squared, the concentration of NO squared, times the concentration of O2. So it would look like that. All right, now we can talk about second order. So second order, you have a bunch of different equations, again, which will be given, and the derivations right here. So the rate is your K constant, your rate constant, times the reactant squared. Now, what we can say is linear. Once you integrate that, you get 1 over A equals KT plus 1 over A initial. So using this rate law, this integrated rate law, we can determine the concentration. We can determine the rate constant if given the initial concentration and then a specific point concentration. We can, at a time, we can determine the initial concentration. We determine a lot of things, basically solving for the unknown. But what we can see from this is that it follows another y equals mx plus b, in that the graph of 1 over the concentration of A over time has a straight slope, and the slope equals positive k this time. And the y, because there's going to be a positive slope, the y-intercept is 1 over the A initial, and it can be used to determine the rate constant, and you can get the T half-life from that. So we're going to talk about half-lives in a minute. Half-life basically means the time it takes for the concentration to halve. And it depends on the rate constant, and it depends on the initial concentration for second order and 0 order. It doesn't for first order. And in this case, the rate constant for the rate constant unit is going to be per mole per second. So it's actually written in 1 over ms, like this, 1 over ms. There is a second order integrated rate law. And then we could talk about the 0 order integrated rate law. Now, in this case, it has a constant reaction rate because if you look, the rate constant equals, or the rate equals the rate constant. There's no dependence on concentration of A. So once we integrate this, it's pretty easy. We can see it's a very simple linear equation that the concentration of A, depending on time, the slope will be negative K again, if it's just the graph of A versus time, plus the initial concentration, which is the y-intercept. Now, think about it. You're thinking about, oh my God, there's all these equations. What do I do? If you see the equation, be able to unravel it. Be able to tell me which type of graph is linear. in this case, there's no natural logs. There's no 1 over. It's just straight up the graph of the concentration of A versus T is going to be linear with a slope of negative K and the y-intercept of A initial. That is very valuable information. And then what you can say is to calculate the half-life, meaning the time it takes for half of the initial concentration to be gone, you can turn A, concentration of A, into 1/2 of concentration of A initial, and then solve for A initial, or solve for T. And then you would get the initial concentration of A over 2K. Again, this will be given as well. But even if it's not, even if just the integrated rate law is given, you should be able to determine half-life by setting A to A initial over 2 and then solving for T. In this case, in 0 order, the rate is what we're more used to in molarity per second because it's identical. The rate is equal to the rate constant. So, of course, they're going to have the same units. In the other cases, we didn't have the same units. We had 1 overs and we had natural logs. So it was a little bit different. So here's the idea of half-life, where after every half-life, half of the original concentration is now removed. So here's a question. The images shown here depict the first order reaction A to B at various times during the reaction process. The black circles represent A and the red circles represent product B. What is the half-life? So the half-life we want to see is, all right, this is initial concentration. Count how many there are and see which image are there exactly half. And then what time is that image? So let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So where are there 5? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. All right, T equals 90. So 90 is the half-life. Here's another one. A first order reaction A to B has a half-life of 25 minutes. If the initial concentration of A is 0.3, what is the concentration of B after 50 minutes? This one you have to think a little bit. So I'll walk you through it. If the half-life is 25 minutes and the initial concentration is 0.3, let's go through some half-lives. One half-life, I'll put HL, is going to give you 0.15. That's after 25 minutes. Now, if you keep reading the question, it says, what happens to B after 50 minutes? Let's figure out what happens to A after 50 minutes. So 50 minutes is 2 half-lives. So after 50 minutes, 2HL, we have 0.075 molar. Okay, so if this is a simple first order A to B, this means if you double the concentration of A, you double the rate, and A makes B. Every mole of A makes 1 mole of B. So it's very straightforward. This means that whatever of A is removed, it will become B. It will be turned over into B and make that reaction happen. So by 2 half-lives, we have the final A remaining is 0.075. So how much B is remaining? We know that the total amount in the vessel or wherever the reaction occurs is 0.3. So 0.3 minus what's left over is how much got converted to reactant or to product B, which would be 0.225 molar. So that's how that would work. So here's a summary on the different rates for 0 order, first order, and second order. Here you have the rate law, the unit for K, the integrated rate law, the straight line slope graph, and then the half-life equation. So you can see how the half-life of the first order is the only one that doesn't depend on the initial concentration of the reactant. It's just the natural log of 2, which is 0.693 over K. And here's just a summary of the kinetics we learned about. And this is just part 1 of the video. We can, part 2, we're going to start talking about the effect of temperature, which is the second important variable relating to reaction rate.